FLIR, F-L-I-R. What is it? How does it work? And why would you want to know? Let's get into it. FLIR, it stands for forward-looking infrared, and it's essentially detecting heat rather than light. So imagine being able to see in the dark or see through thick fog. That is FLIR. So why does it matter? FLIR helps in search and rescue. For example, somebody trapped in a smoke-filled building can be detected using FLIR, or detecting people who are lost in the forests. They can detect the heat of that person. In fact, years ago, I used to fly with the Australian Aerial Patrol, and they had a large forward-looking infrared camera mounted on the front of the aircraft, and they would be called out to go and search for boats and people out in the ocean, sometimes in the middle of the night. And they would be skipping across the ocean at 100 feet looking for heat maps of people or boats, essentially in complete darkness. Now, the applications are just in search and rescue. They are really industrial based and even domestic based, and handheld FLIR cameras can be used by an operator to find faulty equipment. Often equipment goes outside of temperature range or becomes hot when it is not running properly, and thermal imaging is a really great way of detecting if something is operating outside of range. And in your own home, you could walk around with one of these thermal devices and check whether there's insulation leaks or hot and cold spots around your home where you might need to maybe plug a gap or do some work on the insulation. Now, this is way beyond what the human eye can detect. FLIR is the easiest and best way of finding these kinds of problems. A few years ago, we got involved with a company called FLIR, who incidentally were then purchased up by Teledyne, a defense company. And we were working with an even smaller device. This thing was quite tiny, and I have one right here. This is the Lepton. It is roughly 120 by 160 pixels, and in fact it's even smaller than that. It's actually this size. And you can imagine how useful it is to have a thermal imager of this size, being able to put it into many products. Putting it on a drone, for example. We had an application of putting it to the back of a bicycle. Now, as a comparative, this is 120 by 160 pixels, but this camera module here, this is 12 megapixels in the visual spectrum, and this is in the thermal spectrum. So it's important to know that you don't get the kind of resolution that you would from a visual camera. Now, I'm not saying that's not going to change over time, but it'll always be lagging. There's an enormous difference between 120 by 160 pixels and 12 megapixels. Inside a camera like a Lepton camera is a bunch of pixels, and those pixels are made up of a device called a microbolometer. These are sensitive to long wave radiation, and in this device they're uncooled. In other words, they are not requiring some special cooling elements, but they're still sensitive to this long wave radiation, which is in the 8 micrometers to 14 micrometers range. Now, visible light by comparison is in the 400 to 800 nanometer range. So these wavelengths are much longer, and that is one of the reasons that the pixels have to be so much larger to accommodate these larger waveforms from the infrared radiation. Now, every object emits infrared radiation if it's above absolute zero, minus 273 degrees Celsius. So humans emit heat, and the background emits heat, and it's those differences in temperature which creates an outline for a person against the background. The person at roughly 36 degrees Celsius, and the background at, say, an indoor house, it's around 20 degrees or 22 degrees Celsius. So it's that difference which allows the microbolometer to detect whether something is difference in temperature against the background. Now, there's advanced processing that goes on top of that, which pulls out the different colors for the higher temperatures, and that makes it really easy for the user to see something which is a higher temperature compared to a lower temperature. And of course, that heat mapping is something that depends on the application as to how they're going to differentiate the different colors for the different temperatures. So for example, the person who's at 36 might be white versus a 20-degree background, which might be black, and then all the grades in between. But if we're looking at, say, something like a machine, which is going to be running at hundreds of degrees Celsius and the background might be 20, we might need to rescale that heat map. Or just in the same way as we can put an AI model behind a vision camera and a visible light camera, we can put an AI system behind a thermal camera. Of course, the heat maps are different to the visible maps, so we can't reuse the same data sets, but data that's generated from a thermal camera can be used to train a thermal camera AI vision system. So when might we want to do that? Well, there's applications in search and rescue, in health, and in industrial applications. And to take that search and rescue example, can you imagine being in an aeroplane hour after hour staring at a thermal screen looking for a boat or a person in the water? You only have to blink or look away for a few seconds and you might miss them. As a pilot flying for the aerial patrol, which I did for many years, it's very easy to miss. And what they would do is put multiple people observing so that they would potentially reduce that. But an AI vision system would be perfect in that application because it can trigger when it sees something which indicates a person has been detected against the background. That's relatively easy to train and roll out and implement. The limitation being that thermal has many less data points, many less pixels to deal with. And so that needs to be taken into account. So what are the limitations of a thermal system or a thermal AI-based system? Well, some years ago, we used a Lepton device and mounted it to the rear of a camera to experiment with being able to ride a bike at night in traffic and have the thermal images detect vehicles coming up behind. And we found there were a couple of limitations. Firstly, the distance that the thermal could see was very much less than a vision-based system. So our system currently detects up to 220 meters. With the thermal camera, it was much less than that, maybe 20 meters, and that didn't give the rider enough advance warning. The other quite serious issue was that not every car has a different temperature to the background. Now you'd imagine as a car heats up, its engine heats up, and we noticed that the front bonnet, the grille, and even the road underneath would be reflecting heat from the engine. And that was a great sign that there was a vehicle there. But not every vehicle does that. Electric vehicles don't tend to get hot like that. And if a car's been sitting in the ambient environment for a long time, it stabilizes its temperature close to that of the ambient. So we weren't actually able to detect many of the vehicles on the road. There's a couple of serious limitations that we found with using a thermal camera in that application. Overcoming the limitations of the thermal imager can be done by using techniques like sensor fusion, so combining other sensors with the thermal sensor. The obvious one is putting the visible camera with the high resolution capabilities with the thermal camera, the low resolution cameras. This is done in certain devices, which you can purchase even on the local store. And what you could then do is with sensor fusing and run AI separately on those two devices, and then with that fusion technology bring the best of those both together, the high resolution of the visible system and the thermal data from the thermal system, bring those two together and bring those as a complete composite image. That's very powerful for giving a lot more information and overcoming some of the limitations of the thermal system. What is the future of thermal and AI thermal systems? Similar to the vision systems, we're going to see improvements in resolution, in accuracy, and lowering of costs and improvements in performance. This roadmap will continue, and parallel to that will be the advancements in fusion. So bringing other sensors, including the visible spectrum, in and integrating that with thermal systems. Both of those are going to improve in the future, and that's going to mean that we can roll out different and better applications, lower cost applications such as consumer products, for example the Hawkeye cycling product, having it integrated into vehicles, and the improvements in AI as well. As we start generating more and more data off the back of these thermal images, we're going to have more opportunity to train and create better models off the back of that, and specific foundation models based on thermal images, similar to the way we have done so with the vision system. I believe that we're going to see more thermal applications, more fusion technology, and better AI performance, and more applications being developed as we go forward. So in conclusion, what is a FLIR system? It's a forward-looking infrared camera system. It detects heat rather than the visible light. It has some limitations in its resolution, and we believe that can be overcome with AI-based systems tailored to that, sensor fusion, and the roadmap of this technology going forward. I hope that helps, and thanks for watching.